Hello, my name is Lionel Tauszig and I work at EASA on certification of VTOL aircraft. I will be using in my presentation a number of abbreviations, and here is a list you can refer to. VTOL trajectories and vertiports. Why does it matter? If we consider a VTOL aircraft on a vertiport, so the place from which it can land or take off, by definition, a VTOL aircraft is capable of a vertical takeoff or landing. It may be, however, only the very initial portion of the takeoff that is vertical, with the rest of the trajectory being more or less shallow. So if now we imagine urban environments, it could be that if this trajectory is too shallow, it may interfere with obstacles. In such a case, the vertiports have to be moved either further away from the obstacles or have to be elevated. So VTOL trajectories and vertiports matter in that there are elements to answer the following question: what type of urban air mobility do we want? If we are looking for intermodal connectivity, the vertiports have to be close to the streets, the train stations, bus terminals. It may be, however, that if the trajectories are too shallow, those vertiports have to be moved further away from city centers or have to be placed on top of tall buildings. EASA has published technical requirements for VTOL aircraft in a document we called Special Condition VTOL. And I will present a few of these elements that influence VTOL trajectories. The first ones are the safety objectives. For this, we took elements from airplanes where the objectives are proportional to the number of passengers on board. We also took the objectives from helicopters, which are independent from the number of passengers, but are divided in two categories. Category A, where in case of engine failure, the aircraft is capable of continued safe flight and landing, and category B, where in case of such failure, non-scheduled landing has to be assumed. SC-VTOL combines both approaches with a category enhanced, independent from the number of passengers, equivalent to the category A, and the category B with a proportionality according to the number of passengers on board. A novelty we have introduced in SC-VTOL is a link between the categories and the type of operations. Category enhanced is requested for flights over congested area, so what is referred to as urban air mobility. And typically this will be a flight over a city. It is also requested when performing commercial air transport of passengers. And an example would be when you land at an airport, then an aircraft, a VTOL aircraft comes and picks you up and brings you to your hotel. Even if you are not flying over a congested area, you will be then entitled to the category enhanced, and this is what is commonly referred to as an air taxi operation. Basic is for all the other types of operations, for example, a private flight over the countryside. With each category is also associated a performance objective. Category basic, if during the flight you have a failure of a system, then it may be that you need to land right there and then. We, however, request that this landing be controlled, similarly to an auto-rotation for helicopters, and we refer to this objective as a controlled emergency landing. For category enhanced, if you have a similar failure during the flight, then the objective is that the aircraft must be capable of either landing at the original destination, or it must be able to divert to an alternate vertiport. This objective is referred to as continued safe flight and landing. Another element we had to work on is the catastrophic definition. Today, for helicopters, we have a number of different definitions. Some refer to continued safe flight and landing, some to auto-rotation, and we have also references to different numbers of fatalities. So we consolidated all those definitions and introduced some proportionality through the categories. For category basic, multiple fatalities are catastrophic, as are failures that prevent a controlled emergency landing. For category enhanced, one or more fatalities are catastrophic, as are failures that prevent continued safe flight and landing. And for the rest of the presentation, I will focus on this last category. An associated element is the critical failure for performance, or CFP. For helicopters in the category A, we request a minimum level of performance in case of a loss of the critical engine or in case of one engine inoperative. The CFP is the equivalent for the VTOL aircraft. However, while for helicopters in the category A we have mostly 2 engines, for VTOL aircraft we may have up to dozens of them. So the CFP requests to consider single failures, but also any combination that is not extremely improbable. We also extend the concept not only to engines or motors, but to any failures of any systems that affect continued safe flight and landing. And typically this could be a battery. We may also have a different CFP per flight phase and per performance parameter. Another element we had to adapt is the D value. For helicopters, this is defined as the largest overall dimension. And for most helicopters, this is defined by 2 points, the most forward tip of the main rotor and the aft tip of the tail rotor or the tail cone. This D value is used extensively for heliport design to provide obstacle protection. However, specifically for obstacle protection, we are interested instead in the smallest enclosing circle. And as by definition, this is the smallest circle in which the aircraft can fit without hitting obstacles. For helicopters, the smallest enclosing circle is defined by the very 2 same points. So the dimensions are equal and it does not matter if you refer to one or the other. For VTOL aircraft, instead, the situation may be different. If we look at an example of a generic VTOL, the largest overall dimension is defined by these 2 points, while the smallest enclosing circle is defined by 2 additional points. And we can visually observe that the diameter of the smallest enclosing circle is larger than the largest overall dimension. It can be shown that there is a relationship between the two, and this equation means that if we were to use the largest overall dimension for obstacle protection, we may have up to a 15% error. So for VTOL aircraft, we are defining the D value as the largest, as the diameter of the smallest enclosing circle. With all those elements in place, we can now look at takeoff profiles and answer the question we initially raised: what type of urban air mobility do we want? The choice that EASA made was to leave maximum flexibility to the cities and to aircraft manufacturers. For this, we are recognizing 3 different types of takeoff profiles. The first one, called elevated conventional takeoff, starts from an elevated position, which facilitates clearing obstacles, and we allow a dip in the takeoff profile after a critical failure for performance. The second type is called conventional takeoff, and this is more for clear areas where it's easier to stay away from obstacles. Under the conventional takeoff, we also include takeoffs that may have a rolling portion on a runway. As for certain VTOL aircraft and certain types of missions, it may be advantageous to use a runway either for takeoff or for landing and to save energy. Those first 2 types of profiles already exist for helicopters, but we have introduced a 3rd type, specifically for congested urban environments. And we called this takeoff profile a vertical takeoff, as there is a larger portion that is vertical and that can be maintained even after a CFP. All 3 takeoff profiles can be described with common elements, such as a takeoff decision point, which is the point after which the takeoff can be continued, even in case of a CFP. We extend the takeoff profile up to 1,000 feet, and if we look more closely at this portion, it starts when a positive rate of climb is reached, as well as takeoff safety speed. It then climbs up to 200 feet on the first segment, after which the aircraft can further accelerate and climb up to 1,000 feet. Those two altitudes are legacy from the helicopter world, and we will accept different ones, for example, to cater to a different type of in-route structure. On the first segment, we request a minimum climb gradient of 4.5%, and on the second segment of 2.5%. And this climb capability must be maintained even in case of CFP for the rest of the flight, as is the case for helicopters in the category A. As the first two types of takeoff profiles already exist for helicopters, there is existing material for the design of heliports that can be used also for vertiports. One example is the ICAO Annex 14 document, and here is an extract from it describing a takeoff surface that starts at the level of the heliport. Specifically for the third type of takeoff profile, we have developed a new volume for obstacle protection. And here is how this volume is built. So it starts at the level of the vertiport. It goes straight up, and the purpose is to clear nearby obstacles, such as fences, lampposts, or trees. It then has a funnel shape and to give more room for the aircraft to maneuver up to a certain height where obstacle limitation surfaces start for departure or for approach. So we give the opportunity to the aircraft manufacturer to demonstrate during certification that the aircraft can operate in such a volume. Then the vertiport designer can take this volume, add a safety area at the vertiport level, as is done today for heliports, and bring the volume up to provide an additional buffer that can then be used for operation of the aircraft. The aircraft manufacturer is free to provide, to choose the dimensions of such a volume. However, for harmonization purpose, we are also proposing a specific type of volume that we called the reference volume type 1. This reference volume type 1 is foreseen to provide a reference between the aircraft manufacturer and the infrastructure designer in congested environments with a high number of obstacles. This reference volume has been developed by a working group comprising of aircraft manufacturers, infrastructure designers, and aviation authorities. And it has specific dimensions as follows. The vertical portion is 3 meters high, then the funnel goes up to 30 meters. The footprint is 2D by 2D, and at 30 meters high, it's 3D by 4D, from where the obstacle limitation surfaces start with a climb gradient of 12.5%. We have tried this virtual volume in a number of locations throughout the world to see how useful it could be, and I will present one of them. This is Cologne, Germany. The EASA headquarters are located along the Rhine River, next to the central train station. And between our building and the train station, you have a bus terminal and a small square. And we wanted to see how such a volume would fit in the square. So here's the volume with a d-value of 10 meters, and you can see that it clears the nearby hotels as well as the train station. Here is another angle where you can observe the goal of the vertical portion. In this case, it clears a nearby obstacle, a two-story, a temporary police barrack that is on the square. One last view, this time from the ground and looking over the bus terminal. And you can see that this volume is quite compact and fits well in the urban environment. So we think this could be an element to help with intermodal connectivity. All the elements I presented have been published for public consultation, which just finished, and we have received a large number of comments. So we will look carefully at them and make adaptations where appropriate. Thank you for your attention.